If you recall, yesterday we learned these three new basic derivatives. The derivative of natural log of x is 1 over x. The derivative of arc sine x is 1 over the square root of 1 minus x squared. And the derivative of arc tangent of x is 1 over 1 plus x squared. There are other derivatives of inverse trigonometric functions. These are the two that we're going to care about the most. So let's just start with these. The other four are just variations on this theme. So these are just three new basic derivatives that we can include in our combinations of product rule, quotient rule, and chain rule. So we did a little bit of practice with that yesterday. Today we want to look at how we can get at these. So we did the TLDR yesterday with these are the three basic derivatives. This is what you have to have going forward. You have to know the derivatives of these three functions. But we want to think about how we can get at those a little bit today. Remember that arc sine x can also be written as sine inverse x or inverse sine. We'll write sine to the minus 1x, but that will mean specifically inverse sine of x. And similarly with tangent, we'll write tangent inverse of x. It depends on how much space we have and whether or not we can write superscripts or not. One thing that we mentioned yesterday is that not all functions are invertible. We may have to restrict the domain of our original function so that we get a function. So when we think about sine, the sine function, we know that that's not invertible. There are an infinite number of x's that produce a particular y value. So for sine, we restrict that to the first and fourth quadrants. We only need two quadrants that are connected together that have positive values and negative values. Sine is positive in the first quadrant, sine is negative in the fourth quadrant. So we restrict our domain of sine from negative pi over 2 to pi over 2. That's how we get an invertible function. It was similar to what we looked at yesterday. When we invert x squared with the square root of x, we have to restrict our domain to either positive values or negative values. So details aside, let's get into some mechanics of where these come from. So remember that inverse function means that f inverse of x should be f inverse of f of x equals x. If we apply a function and then the inverse function, we should be back to where we start. Start with x, do f of x, then do f inverse of x, you'll be back at x. This is what we mean by an inverse function. Natural log of x is the inverse of e to the x. Natural log of x is the inverse of e to the x. So if I do e to the natural log of x, I get x. Natural log is the logarithm base e. So natural log of x is the power of e that's equal to x. So it makes sense that if I take e and raise it to the power of e that's equal to x, I get x. So what we're going to do is take this equation and we're going to find the derivative of both sides. On the left, we're going to use the chain rule, and we're going to pretend that we don't know the derivative of natural log. On the right, if these two functions are equal, then their derivatives must be equal. We'll take the derivative with respect to x. We're going to take the derivative of both sides, pretending that we don't know the derivative of natural log of x is 1 over x. We're going to start with something that we don't know, or that we know, and we're going to generate something that we presumably don't know. I did the TLDR yesterday. I had a spoiler yesterday. Probably should have been like all spoiler alert, the derivative of natural log of x is 1 over x, but I didn't. No one came after me online, so I figure I'm safe. So on the left, we're going to take the derivative of e to the natural log of x. So we're reading this as the inside is natural log of x. And we're pretending that we don't know the derivative of the inside, and we're reading the outside as e to the stuff. So the derivative of e to some stuff is e to that stuff times the derivative of that stuff. And that's what we're pretending we don't know. So we would multiply by the derivative with respect to x of natural log of x. Once again, we're pretending that we don't know this. So we get e to the natural log, the derivative of e to the natural log of x is e to the natural log of x times the derivative of natural log of x. On the other side, we take the derivative of x and we get 1. What we're trying to figure out is the derivative of natural log of x. On the left, we have the thing that we're looking for, the derivative of natural log, and we have this factor of e to the natural log of x. We're no longer using this form, so I'm going to simplify e to the natural log of x. I'm going to replace that with x. And so this tells us that the derivative of that x times the thing that we're looking for that we wrote because of the chain rule is equal to 1. So that tells us that the derivative of natural log of x is equal to 1 over x. So that's how we could use the property of inverse functions, or how inverse functions work, not property, how inverse functions work to get at the derivative of natural log of x is 1 over x. Really, I just needed to take a second today where I spend a lot of time saying shit like the derivative of natural log of x is 1 over x, because I need that to be stuck in your head. The problem is I'm going to say that too much, and it's going to get stuck in your head so much that if we try to do this backwards, you'll be like, oh, the antiderivative of natural log of x is 1 over x, because you heard derivative of natural log of x. But that's a problem that we can fix later. Questions? We do this with all of these. So we do this kind of thing with all of these. So for example, notice what we're doing is we're setting up, to use this property, we're setting up the inverse function as the inside, because the chain rule will pop out a derivative of the inside, and then we can solve for that later on. Let's try this with tangent. So the setup is going to be, we'll take the tangent of the arctangent of x is equal to x. Once again, we're going to take the derivative of both sides, pretending that we don't know the derivative of arctangent. Do the same thing that we did before. We're setting up the thing that we're looking for, the derivative of the inverse function, as the inside. So our inside is arctangent. And our outside function is tangent. The reason I wanted to do this one, in addition to the e to the x, the natural log of x one, is that this one gets a little bit messier. I want you all to, all of you who had skipped trig, to remind you to go brush up on your trig. Right now, like in class, there's not going to be a quiz on trigonometry, so we're just like, oh, pretend. I was like, I totally remember all of trig, but that's just not always the case, especially in Calc 1. I landed in a Calc 1 class having a sum total of 3 weeks of trigonometry. So, and my Calc 1 professor's like, oh, hey, you remember trig? I'm like, oh, yeah, totally. There was only like 3 weeks of it. And he's like, oh, double angle identities. I'm like, oh, excuse me, what? So some trig is going to happen here. We're still going to do the same thing. We're going to take the derivative of the outside with respect to the inside and then multiply by the derivative of the inside, which we presumably don't know. So the derivative of tangent of a thing is secant squared of that thing times the derivative of that thing, which we are pretending that we don't know. On the other side, the same thing happens. At least we can count on good old x to have a derivative of 1. So I'm just using the chain rule on the left. Now, when we look at this secant squared of arctangent, that doesn't simplify like e to the natural log of x. We can solve this. We can solve this for the derivative of arctangent by saying 1 over secant squared of arctangent of x. We can even rewrite the secant of secant 1 over. We can even write 1 over secant squared as cosine squared. So let's do that. The thing that we're looking for, pretending that we don't know it. Hang on, pen cap went flying off. Pretending that we don't know the derivative of arctangent, we can write the derivative of arctangent is 1 over secant squared of arctangent. And right now you're looking at this and saying, dude, that does not look like 1 plus x squared, even though it totally looks like 1 plus x squared. I told you y'all didn't remember your trig. I'm just kidding. It doesn't look like 1 plus x squared yet. We can write this 1 over secant squared as cosine squared. but this is still of arctangent. And now it doesn't even look like the 1 over part. The problem is this, I have cosine of arctangent, and I can't just cancel those out. If I had tangent of arctangent, those just cancel out and I get x. If I had sine of sine inverse, those would just cancel out. But I've got cosine of arctangent. Even worse, I've got cosine squared arctangent. That doesn't matter, the square came next. Why didn't you catch that? Minus 1,000,000 points for everybody. I'm just kidding. I didn't give you a chance. Doesn't matter that it's squared. We've got cosine of arctangent. That's not acceptable. This is not a good way to write this. Next semester, when you're in Calc 2, you're going to find out this is still not a good way to write this. You can't be like all cosine of arctangent. Here's what we know. Arctangent is an angle. When we look at arctangent of x, we read this as an angle in a right triangle. We want to read this arctangent x as an angle in a right triangle. The tangent of this angle is equal to x. It's an angle in a right triangle, and the tangent of this angle is equal to x. So I'm going to set up a right triangle where the opposite is x and adjacent is 1. This tangent is opposite over adjacent. We're going to read arctangent of x as an angle in a right triangle. The tangent of that angle is x. I'm going to read x as x over 1, so that's opposite over adjacent. So now I can write the cosine of theta. I can figure out the hypotenuse. The hypotenuse will be 1 plus x squared, square root of 1 plus x squared. And now I can write an expression for the cosine. Cosine of theta is therefore adjacent over hypotenuse, 1 over the square root of 1 plus x squared. Therefore, the cosine squared is 1 over 1 plus x squared. There's a few things going on here, most of which are algebra and trigonometry. The only calculus that we've had in this example is the chain rule. And the derivative of tangent of something is secant squared of that thing times the derivative of that thing. A quick note on perspective, because students watch math done in very strange ways. I will never ask you to derive the derivative of arctangent in this fashion on some test. That would be a weird question. It might show up on the homework. I can't remember what I assigned for homework. made homework assignments a long time ago, and I just keep running with it. So there might be some messed up problems on the homework. But I would never ask you to derive the derivative of arctangent. I would just expect you to know the derivative of arctangent. This was really just algebra and trigonometry. Algebra because, hey, remember how inverse functions work? And trigonometry, partially trigonometry aesthetics. It's unacceptable to write cosine of arctangent of x. We've got to fix trig function of inverse trig function. That has to be fixed. And so we have to go into, we can use right triangles to fix it. It's unacceptable to have trig function of inverse trig function and just leave that as an expression. Actually, it doesn't have to be another one. So it's unacceptable to leave a trig function of some other trig function as an expression. The interesting thing about this trig function of inverse trig function is that we have this composition of transcendental functions, and it will pop out an algebraic function. So this composition of transcendental functions is popping out an algebraic function. That's pretty neat. Happened with e to the x and natural log of x. That was a composition of transcendental functions, popped out an algebraic function. How's everybody okay? Transcendental functions are all the functions that aren't just like polynomials and radicals and math. That's why the book's called Calculus, Early Transcendentals. And you're like, oh, ooh, this sounds like it's going to be some meditation or something like that. It's like, oh, no, that's just what we call those kinds of functions. Any questions? Comment? Snyder remark? We had an articulation issue at one point because, with our Calc 2 class, because in the description of the Calc 2 class, it's like all integration of polynomial, rational, radical, and then we just listed all these transcendental functions: exponential, logarithmic, trigonometric, inverse trigonometric, hyperbolic trigonometric functions. Listed all those, and then we sent that off, and then we get articulation problems from other schools. I thought, you didn't cover transcendental functions. I thought, what? And I look at the list and I go, dude, we listed them all. And then I realized what it was. We didn't use the word transcendental. We fixed the problem by just saying transcendental functions such as, and then put that right in front of the list. Didn't have a problem after that. That's when I realized that articulation officers don't have to know calculus. I'm not saying that they should. That would be an unreasonable ask. It would be 100% unreasonable if your articulation officer has to understand fucking calculus. Not a big percentage of the population understands calculus or can do calculus to the level that you can do calculus, even like right now. By the time you finish multivariable calculus, you will be in maybe generously top 10% of the world population in mathematical ability and knowledge. I'm not fucking kidding. There aren't a lot of people that have this kind of knowledge, and we're just like giving it to you. We don't let you leverage it into like a fabulous career, because why would we do that? Why would a billionaire like myself want some other billionaires running around chipping into my profits? I'm just kidding, I'm not a billionaire. Any questions? Comments? That's what we have to tell you to keep the truth. Try to convince you not to be too. Make big piles of it. I'm just kidding. Yes. Oh, that's therefore. So the three dots like this is an abbreviation for therefore. Everybody okay? Many times I will use symbols because there's a lot of common abbreviations in math that you haven't seen before. And the way you get introduced to them is not someone telling you what they are. Someone just starts using them on you. And you're like, write them down in your notes. And you're like, oh, what the fuck is that? Oh, that's therefore. Like, remember the definition of a limit? We can write the definition of a limit by saying, first of all, this is an abbreviation. Limit as x approaches c of f of x equals L, if and only if for every epsilon greater than 0, there is delta greater than 0, such that absolute x minus c less than delta implies absolute f of x minus L is less than epsilon. Because that's too many words to write, so we just use these symbols. And then we don't tell you what the symbols are because we're dicks, I guess. So IFF, that's an abbreviation for if and only if. I think I've told you that one before. Have I told you that one before? That's an abbreviation for if and only if. Fun story, I had one of my professors wrote a combinatorics book. Combinatorics is math word for counting. He wrote a book on counting. It was a graduate level textbook, but it was about counting. And he just used abbreviations for a lot of it. So like all throughout the book, there's like all this A, if and only if B, right? Because it's an if and only if statement. And the publisher was like, oh, look at all these typos. And they changed every if and only if to just if, fucking up the entire meaning. Because A, if and only if B means those two have to be the same. A, if B, completely different. So he was like looking at it, it's like, oh, wow, this looks great. There's some F's missing. And then he looked at the editor, I'm like, oh, and I know who's getting them. Anyway, so IFF, that's an abbreviation for if and only if. That's just a bidirectional implication. The upside down A, that's what I was trying to draw here in front of the epsilon. That's an upside down A. That's an abbreviation for every or for all. And it is just an upside down A. Greater than 0, you have to know that one. The backwards E is there is or there exists. So that's just a backwards E, and we say that, we pronounce that there is. Or there exists. The backwards euro symbol, it's not really a backwards euro symbol. It's like a C with a little in it. It's like a combination of a C and an uppercase E, or it's a lowercase backwards E with its face cut off. That'd be a more American way because that's more violent way to describe it. That's not as common, but that's a symbol that I use for such that. It's a backwards is an element of. This one is less common, so this one's a little bit sketchy, but we read that as such that. I'm still not sure if my analysis professor in graduate school or upper division and work in graduate school was fucking with us when he did that. Or if he just made that up himself and convinced us all that that was super common. And then the arrow is and implies. So the implication is an if A, then B. So A implies B is how we would use that. So if we see A implies B, if we just want to read the symbols from left to right, we might say A implies B. But we might also say if A, then B. If A is true, then B is true. Any questions? How's everybody okay? I mean, you remember that from your symbolic logic course, right? I'm always curious. Sometimes I want to grab like a test or something like that or a quiz and put symbolic logic on it just to find out. Because randomly, like 1 or 2 students every couple of years show up and their teacher in high school like taught them symbolic logic. And I'm like, oh, whoa, what is your teacher's name? That is fascinating. And I show up at the school. I'm like, oh, I'm looking for a math teacher. Oh, sir, this is a high school. This is the United States. You have to leave. I go, but I need to know. Find me this math teacher. It's the symbolic logic as I'm being hauled away in the police car. And then Pacific was like, well, you can't come in the city limits anymore. I'm just kidding. I'm not banned from Pacifica. I'm banned from South City. I'm just kidding. I'm not banned from South City. Restraining order expired. I'm just kidding. It's still in effect. I'm just kidding. There was never a restraining order. Those records were sealed. I'm just kidding. You couldn't seal something like that. It's a restraining order. It's public information. There was no restraining. All right. We could do a similar thing with arc sine. You would set it up as sine of arc sine equals x, pretending you don't know the derivative of arc sine, and you would have to do the same maneuvers. And you can see what's going to happen, right? Eventually, we're going to have, it's going to say arc sine of x, and we're going to read that as an angle with an opposite of x and a hypotenuse of 1. And so down here, it will have an opposite of x and a hypotenuse of 1. And down here, we'll have a square root of 1 minus x squared. That's where the square root of 1 minus x squared shows up. The square root sticks around because the derivative of tangent is secant squared, but the derivative of sine is cosine to the first, just 1 cosine. So, comments, snide remarks, deep thoughts? How's everything? Is calculus super easy? In big news, we have a 4-day weekend, so there's no class tomorrow and no class on Monday. I'm sure everybody's super disappointed about that. So in other news, I didn't make copies of the problems I was going to have you do today. So that's going to do it for today. I will see you all. That's going to do it for this week. I will see you all on Tuesday. Everybody have a good long weekend. Try not to forget everything that we've talked about this week. And thanks for playing.